So in this video, to illustrate the use of mathematics throughout human history, I'm going to talk about numbers and how people invented bigger and bigger sets of numbers and use them in the real world to calculate things and to make sense of what's going on. All right? So in the beginning, there was counting, and it was good. People were able to say, here are some apples, here are some bananas. I can take a set of 3 apples, or I could take a set of 3 bananas, and it doesn't matter that this is apples and that's bananas. Even though the fruits are different, they taste different, right? They're different types. They have different color. They have different size maybe. But the size of the sets are the same. Here's 3 apples and here's 3 bananas. And because they have that in common, then whatever I say about the 3 apples that has to do only with the number of things in it, the same thing can be said of bananas or any other set that has the number of things in it. That was the first insight. Numbers themselves are an abstraction. It basically says we don't care about what type of objects they are inside the set. We only care about the number of things. Of course, people didn't necessarily think about sets 5,000 years ago this way. They didn't have set theory, something that was invented in the 19th century. I'm going to talk about in other videos. So it wasn't formalized, but even if they weren't aware of it, intuitively, they were using these concepts. That's what I'm going to describe here. So a set of things, one of the things you got to do is be able to describe unambiguously what's in the set. Now, if I've got a set of, let's say I've got a bunch of apples lying around, a whole pile of apples, and I point to 3 of them and I say, these 3 apples, right? Someone's not nearby or they can't see them. They're not sure which 3 apples I'm talking about. So when you're talking about a set in mathematics, you have to have a rule that anyone who you're talking to can apply that same rule and unambiguously figure out if an object is in the set or not. I can have a set of an apple plus this banana and this apple, okay, and that's what is in that set. But in order to do that, I have to communicate that to whoever I'm speaking to. Mathematics is a language that has, among other things, notation. Standard notation, so that when I write something in math, anybody else that reads that should be able to understand right away what I'm talking about. And all the things that are irrelevant, like the type, the color of the banana, that stuff they don't have to agree on. But they do have to agree on how many members there are, for example. Another concept that people used, even though they weren't aware of it, is variables. Variable, as a concept, is that you can take any item from a given set. It doesn't matter which item. So here I've got 3 apples. They're different color, they're different size, pretty much the same color. Different size, different taste maybe. But I can say, let X be any apple. Let X be a member of this set A, any member. Or I could say, let Y be any banana, right? Let Y stand for any member of this set. And then I'm going to say something with X and Y, right? So variables, that's the concept. And the nice thing about variables is that it's a second level of abstraction. Because now when you've got sets, not of apples or bananas, but you've got sets of numbers, you can have X stand for any number in that set. Let's go over a few sets that people have used throughout history, and then we're going to go and really talk about what made people need to invent these sets. So the first set is a set of natural numbers. People used it thousands of years ago. They figured out that you could say this is the first object, that's the second object, that's the third object, right? Or they could say, I've got 1 apple, and I've got 2 apples, and I've got 3 apples, right? So there's 2 variations today, natural numbers. The set is the bold letter N. There's 2 variations. Computers, usually people that deal with computers, they put 0 in the set. So it could be 0 numbers, 0 apples. Sometimes they don't. Some people don't put 0. We're going to put 0 in the set of natural numbers. So 0 is going to be counted as a natural number. So natural numbers are just 0, 1, 2, 3, 4, 5, 6, 7, and so forth. 1,000,000 is a natural number. -1 is not a natural number. -1 is something that was invented later. Negative numbers represent things like debt. And initially, people might have thought, what does that mean, -1 apples? We're going to talk about that. Integers are represented as the bold letter Z. That's because in German, the word for integer starts with Z, and it was German mathematicians that formally talked about set theory in the 19th, 20th century. So Z got to be the letter that represents integers, which is all the counting numbers, which I mentioned, all the natural numbers, and all the negatives of those numbers. Now, rational numbers are numbers that can be represented as a ratio. They're the fractions. They're a ratio of P to Q, P divided by Q, where P is a natural number, Q is a natural number, it's not zero, right? It's the denominator. So basically, this is what the notation says mathematically, unambiguously. Let P be any natural number and Q be any natural number that's not zero. Then P divided by Q, the set of all those things, are the rational numbers. We call that set Q. Then we're going to talk about real numbers. And finally, we're even going to talk about imaginary and complex numbers. People invented in the last, I'd say, 600, 700 years. So let's get started. Okay, so first of all, you've got natural numbers. Remember, each variable has to come from a set. So let A and B be natural numbers, right? You can define an operation on these two numbers called addition. You can add two numbers together. And people obviously figured out some properties of addition long ago. One property is that it's commutative. That means if I start out with 3 apples and I add 2, I'll get 5, right? And I'd get the same thing if I first started out with 2 apples and I added 3. And the way to prove that, because in math, you have to be able to prove everything. Not you specifically, maybe, but the proof has to be there. Otherwise, it's not a mathematical, not a proven statement. It could be false. So this is a true statement, so here's the proof. Here's a geometric proof. Now, a proof is in terms of something else. So if you're an ancient person and you want to prove that 3 plus 2 is 2 plus 3, or more generally that A plus B is B plus A, then you could do it this way. You got the 3 apples and the 2 apples, right? And if you flip this kind of 180 degrees, right? If you flip it, you get 2 apples plus 3 apples. You still have the same apples, but you got B plus A instead of A plus B. It's interesting that in Hammurabi's stone tablets, and they had in Sumer, they didn't have A plus B or B plus A. They didn't have variables. They gave you examples. Examples like, hey, 3 plus 2 is 2 plus 3. 4 plus 7 is 7 plus 4. And you were supposed to get the idea. So today's math is more efficient. And of course, over time, we built up this machinery. Multiplication is another operation. Multiplication is repeated addition. So what that means is, you've got one person with 3 apples. Then you got another person with 3 apples, let's say. That's 2 people, each with 3 apples. So 2 times 3, right? It's 3 plus 3. And that's what multiplication is. I know I'm belaboring these points. Like, of course, that's what multiplication is. But I'm building everything up from scratch to sort of show you these sets of numbers and how people started to need bigger and bigger sets of numbers that they didn't have before. So right now we're starting small. We're starting with just the counting numbers, and we're able to add them and multiply. So multiplication also has the same property as addition. A times B is B times A. How do you prove that one? Well, here's a graphical proof. You have a rectangle of a grid of 2 by 3 apples, and if you rotate it 90 degrees, you're going to get a grid of 3 by 2 apples, right? Just like that icon says. So you started with the same apples, you ended up with the same, you just move it around. You can turn your head, right? And you can prove it that way. Now, the distributive law is how multiplication interacts with addition. And that happens because multiplication is repeated addition. So the distributive law, you probably saw this in algebra, is A times, and you do the addition, x plus y. So you do the addition first, x plus y, and then times A. Or you could do A times x and A times y, and then do the addition. So you could either do the addition first, then multiply by A, or you could multiply each one by A and then do the addition. That's the distributive law. And on the right, you can see the proof. You got a grid here of 2 by 3 apples and another grid of 2 by 2, right? So if I move and if I bring those two together, I'm going to get a grid of 2 by 5, which is, I did the addition first on the bottom, right? You got 5, and you got 2 times 5, that's 10 apples. The other way, right? The other way I could have done that is I first multiplied 2 by 3, and then I also multiplied 2 by 2, and I got those totals, and then I added those together, and I'd still have 10 apples. So that's how you can prove the distributive law if you're an ancient person and you are, and look, now you've got these two operations. You could do addition and multiplication, and they have these properties. So you can actually do algebra and simplify, just a lot of equations into like simpler equations. You got this complex task, and you can break it down into addition and multiplication. If you can do that, that's pretty cool. You can do a lot of things with these. And then people got even bigger numbers, and they invented raising to a power. So let's say n is a natural number, 0, 1, 2, 3, 4, 5, something like that. You can raise any number to the power n by multiplying itself by itself n times. So a to the first power is a. A to the second power is a squared. A to the third power is a cubed, okay? It's called squared and cubed, by the way, because ancient people figured out that if you want the area of a square, the number of square feet in a 3 by 3 would be 9, a 3 foot by 3 foot thing. And it's cubed for the same reason. You just multiply the side by itself 3 times and you get the volume of a cube. So that's why a squared and a cubed. But you can raise a to any natural number power by multiplying itself by itself n times. If raising to a power is repeated multiplication, just like multiplication is repeated addition, right? You should expect to have similar properties on how raising to a power interacts with multiplication. The same way that multiplication interacts with addition. So let's see that. Here, we've got a grid of A's, of numbers. Instead of the objects, we go up one level of abstraction, we're going to have numbers. So no matter what number A is, there are m times n A's over here. Okay, it's a grid of m by n. So if you multiply all those out together, you could see that you could either first of all raise a to the m power, that's like a row, and then do multiply by n columns, multiply that result n times by that by itself. Or you can group the a's by column first, which then you have n of them, and then you basically have m columns, and you group them that way, you still get the same result. So a to the m and then to the n is the same as a to the n and then to the m, which is also the same that if you multiply m by n first, you get the number of entries in this grid, and then you raise a to that number of entries, right? Then a is multiplied by itself that number of times. So all of these are equal. A to the mn, a to the m, and then to the n, a to the n, and then to the m. Finally, you got sort of like the same thing as the distributive law. Remember we had here that you could do addition first, and then multiply by a, or you could first multiply by a, then do addition. So similarly here, you could add the powers and then raise a to the result, right? Or you could first raise a to the first one and multiply by raising a to the second one, right? If you combine that, you're just going to get the thing on the left. So raising to a power is yet a third operation that you can do, and interacts with multiplication. It is to multiplication the same as multiplication is to addition. So it's almost like the next level of algebra on n. You have all these operations, okay, but it turns out that with these operations comes problems. What sort of problems? Well, here's one. How do you solve this equation for a? A is a variable. Let's say a comes from natural numbers. Remember, every variable needs to come from some set. So let's say it comes from the set of natural numbers. No a in natural numbers can satisfy this equation. A plus 5 equals 3. Well, that's negative 2. But negative 2 hasn't been invented yet, right? So here we got this guy. He's saying, look, I want to go up 5 feet, and I want to be 3 feet above sea level in the end. So where am I now? The answer is I'm 2 feet below sea level. Negative numbers can represent things below a certain level. It's 0, right? They can also represent debt. For example, that you owe someone money or something like that. They can represent negative temperature below 0 Celsius or 0 Fahrenheit. These are examples of uses of negative numbers. So people invented negative numbers, and the set of negative and positive whole numbers is called integers. It turns out we could do the same algebra we've been doing with integers that we could do with natural numbers. We can add them, we can multiply them, but we could also subtract now. So here's a few more concepts that people came up with. Again, many of them didn't explicitly say it like this, like we do here, but these are the tools that they used. So first you have 0. 0 is the additive identity. What that means is you take any number and you add 0, right? You still have that number. So with respect to the operation called addition, 0 doesn't change any of the numbers. You just add it and it's still that number. That's why it's called the additive identity. So we will define the negative of A as be minus A. All right, that's how we're going to write it. What that means is it's a unique number that when you add A and it's negative together, you're going to get 0. So 3 and negative 3 added together gives 0. 10 and negative 10 gives 0. See, every number has a unique negative of it that you can add and get 0. Okay? So we can then, using these concepts, define subtraction. Subtraction is going to be adding the negative. So A minus B is going to be the same as adding the negative of B. All right, and here you have an illustration. If you got 6 minus 2, that's the same as 6 plus negative 2. All right? Negative 2 is now a number. It's fully integrated into the system where you can add it to any other number. It's like subtracting its negative. Okay? That idea, you can expand your number, your set of numbers, and your number system, and you can expand your algebra to work with the previous set, but also work with the new set seamlessly. Okay? That is what people started to do. They started to get larger and larger sets of numbers. And by the way, this notation over here means absolute value. Probably heard about this already. That's how far a number is from 0. So 4 and negative 4 are the same, they have an absolute value of 4. That's the distance from 0. They're the same distance, which is 4 units. So on this journey through mathematical history, we've seen people take the natural numbers and expand this set to the integers. And then they could take the algebra and expand it to work on all the integers seamlessly as they did for natural numbers. And they introduced subtraction. Well, it turns out people still had equations they couldn't solve. For example, A times 5 equals 3. What is A? A times 5 equals 3. Of course, we know you can divide 3 by 5. But division needs to be defined. So here's how we define division. Similarly to how we did with subtraction. So 1 times any number is that number. So 1 is called the multiplicative identity. With respect to multiplication, if you multiply by 1, you get the same thing back. The reciprocal of A will be 1 over A. It's the unique number that when you multiply A by it, it'll get 1, right? They cancel each other out. The same way as we had with the negative, and you add them, you have with the multiplicative inverse, the reciprocal, and you multiply them. Also, the reciprocal is denoted A to the minus first power. That's because when the powers add, remember, when you have here the addition of m plus n, right? And you multiply 3 and 1/3, you're going to get 1. So if you have m and n are negatives of each other, then a to the m and a to the n are reciprocals of each other. See how that works? So people figured this out and they made fractions. The Pythagorean school, 2,500 years ago, were really pleased. They really believed that the whole world, a ratio of any length to any length, all you had to do was subdivide into enough pieces, and then they would have these nice ratios of things. They have the golden ratio, which I'm going to talk about in other videos. So the Greeks already used fractions, and they used negative numbers, of course. And then something interesting happened. But before I tell you that, I just want to reiterate again. Dividing by a number means multiplying by its reciprocal. The same as subtracting a number is adding its negative. Right? So dividing by a number is multiplying by 1 over that number. And that's how we extend algebra to the rational numbers. But it turns out some numbers on the real number line, like these over here, are not rational. You cannot express these numbers as a ratio. To see this, let's first talk about the Pythagorean theorem. 2,600 years ago, the Greeks already were good with geometry. And they related some of the algebra and variables to the geometry. So say you've got this triangle, they would say, and it's got lengths A, B, and C. It doesn't matter how big it is. It's just that it's a right triangle, so the two sides are perpendicular, they form a right angle. And then you've got the hypotenuse. So they figured out that A squared plus B squared equals C squared, right? A times A plus B times B equals C times C. And here's the proof. Again, every mathematical statement, in order to be sure it's true, you got to prove it. Otherwise, you're never sure. So here's how the Greeks were able to prove it. Here's one way. Take this triangle and make 4 of them. All right. So you got here on the left, you got the 2 blue ones and 2 red ones. Right. That's 4 of them. Now look at the sides. What are the sides of this yellow square? B times B. Right. B squared. And the green square is A times A. It's A squared. So we got A squared plus B squared. Right. The area plus these 4 triangles. Now look on the right. We rearrange these 4 triangles. Right? They're the same triangles, the blue, 2 blue and 2 red. But we rearrange them in such a way that inside we form a C squared square. So if the outer square is the same size, then A squared plus B squared equals C squared. So that's how you can prove the Pythagorean theorem. The Pythagoreans really thought that mathematics could explain a lot in nature, and they really thought that you could subdivide things, and every length had a ratio to every other length. But they were wrong. One guy in Greece was able to show that there are numbers you cannot express as a ratio of one integer to another. Check this out. Here's an algebraic equation. A squared equals 2. A times A equals 2. Now we start talking about square roots. Look on the right. You see area equals 2, right? So what's the side of that square? If the area equals 2, what's the side? It's square root of 2. Another way to look at this is the Pythagorean theorem. Here is a right triangle, an isosceles right triangle. That means it's got the sides are the same, 1 and 1. And so the hypotenuse must be the square root of 1 plus 1, which is the square root of 2. So I'm not going to prove it here. You can look at other videos. But it's pretty simple to prove with prime numbers. That the Greeks also knew about prime numbers. Turns out that the square root of 2 cannot be expressed as a ratio of any 2 integers. So that means if you've got a ruler that measures the side of this triangle right here, that same ruler, let's say that side was an inch, you could subdivide that inch into 1,000,000 billion subdivisions, as long as they're all equal. That square root of 2 cannot be measured with any subdivision of equal parts. It will always, it will fall somewhere in between. So that's an interesting result. No matter what denominator it is and what numerator it is, you can't express one length in terms of subdividing the other. And the legend goes that the man that invented this, that showed this, proved it to the Pythagoreans, And since the proof was airtight, they were not very pleased. He met an untimely death by being thrown overboard in a ship. Now, whether he was thrown overboard by people or whether he just fell overboard, he was thrown over by the waves, we don't know. But the legend goes that they were not very happy. Now, let's go back to our numbers, however. If we are here, when we talked about negative numbers, integers, we were able to talk about subtraction. When we talked about rational numbers, we talked about division, which is the opposite of multiplication. So what would be the opposite of raising to a power? That would be taking the root of that power. So square root is the opposite of squaring. Cube root is the opposite of cubing. And in general, you could have something raised to the 1 over n power, raised to a fractional power. And if you raise to fractional power, like 1 over n, and then you raise the result back to n, you get the original number. Because the powers, they multiply. And it turns out there are many, many irrational numbers. Another irrational number is pi. Pi is the area of a unit circle with radius 1. Its circumference is 2 pi, okay? And the Greeks knew this as well, over 2,000 years ago. And it turns out that pi is irrational also, which means if you take a tape measure and let's say you've got a cup and you measure around that cup, the circumference, right? Whatever number you get, let's say that number comes out to be exactly 1 inch around or exactly 5 inches around. That unit, no matter how you subdivide it, won't be able to measure the radius. The two quantities are incommensurate, they're called. In other words, you can't use the same unit to measure both the radius and the circumference of a circle. Interesting, huh? You can't square the circle, they say, and it's true. So, if you took all the rational numbers and you put them on a line, you have 1, you have 3 halves, you have 7/5, and so on. If you plotted all those as dots on a line, you'd have holes between the dots. Even though, this is interesting, the dots can be as close as you want to each other. There's always, between every 2 rational numbers, there's always going to be another one. So they're very dense, as they say, infinitely dense. And yet, there are some points on the line that are not covered, like square root of 2 and pi, right? So it turns out if you fill in all the holes between those numbers, if you put all the rest, the irrational numbers in there, the rational plus the irrational numbers, you get the set of all real numbers. And that line, that's called the real number line. And that's a continuum. It's a continuous line. It's a set that is strictly bigger than the set of rational numbers because there's more numbers in there. How many more? We're going to cover that in another video. Uncountably more. So for thousands of years, people were using these real numbers. They were adding and subtracting, multiplying and dividing, raising to powers, and taking cube roots. And things were good. But there were still some algebraic equations that you couldn't solve. This pushed people to expand their number line yet again to a larger set of numbers called complex. This set generalized all the previous numbers and enabled you to solve equations like this one. A squared equals -1. What real number can you multiply by itself to get a negative number? Well, we all know that positive times positive is positive. And negative times negative is also positive. But how are you going to get a negative number? So again, once again, we expand our number set to include imaginary numbers. This happened only about 600 to 700 years ago, that people started systematically analyzing algebra on this larger set of numbers. They're called imaginary because people thought, hey, these numbers don't really exist. I mean, look, if you graphed a squared, if you graphed y equals x squared, then the graph of all the y values would be above the 0, right? They're all positive. So how would you get the negative values? Well, someone said, suppose there is a number called I that's the square root of 1. Let's see if we could do algebra with that, I. And let's see if it fits in, and maybe you could get a larger set of numbers with I that consists of all the real numbers, plus all numbers you could get by adding I and multiplying I by real numbers. So that's how this would work. It turns out this algebra works perfectly well. And this algebra will help you to solve equations of that form. So here's how the algebra works. Each complex number has a real part and an imaginary part. Here, the real parts on the left side in algebra are black, and I've put the imaginary parts in purple to kind of separate them visually. So this is how you would add two complex numbers together. A plus bi, that's one complex number, plus c plus di is another complex number. You would simply add the real parts together, and you'd add the imaginary parts together. How do we know? Because we can just do the algebra and rearrange the terms by commutativity of addition. And we group the I terms together, and then we use the distributive law to take the I out of the parentheses, and that's how we get this result. For multiplication, we multiply just as we would with algebra. So A times C, there it is, A times C. And then look at this, we can do BI times DI. That's B times D times I squared, which is negative 1. So that plus turns into minus. So we've got AC minus BD. Then we've got two terms with only one I in them. We've got ADI and we've got BCI. And by associativity, you can take the I out of the parentheses. And look at that, we've basically multiplied two complex numbers together. The real part of the result is AC minus BD. And the complex, the imaginary part is AD plus BC. But whatever it is, that's how you define addition and multiplication of complex numbers. 1, the real number 1, is still the multiplicative identity because any complex number A, remember, a variable has to come from a set. So any complex number A times 1 is still A. 0 is still the additive identity because A plus 0 is still A for any complex A. So this algebra still works, and the commutative and distributive laws still apply. In the 1570s, a mathematician was able to systematically describe this algebra on complex numbers. So over 2,000 years since people invented the rational numbers, and then proved that they didn't have the real number, that not every real number is rational, that there's irrational numbers. After all that, after around 2,000 years, they invented this set. And why did they do it? Because you have these algebraic equations where you have squaring, and you sometimes want to be able to solve each algebraic equation for A. These algebraic equations are called polynomials. Let me show you how the algebra on complex numbers works graphically, just like I did before with other number sets. So adding two numbers together, whether they're real or complex, is like adding two vectors together. A vector is like you've got a distance and a direction, just like this arrow here. So imagine that this arrow, it's like going to the right by 2 units and then going up by 3 units. That's why that point there has a real component, a real part of 2 and an imaginary part of 3. So if we added two complex numbers together, it would be like putting two arrows end to end. If I multiply this number by 2, it would be like putting another arrow just like this one and putting them end to end. So I would go again to the right by 2 units and up by 3 units. So overall I would have gone 4 units to the right, 6 units up. And you can see how that works. Multiplying by real numbers, just multiply the real part and imaginary part by that number. Okay, what about multiplying by imaginary numbers? Well, multiplying by real numbers stretches it, right? If I multiply by 2, it doubles the length. If I multiply by -1, it kind of reverses the direction of the arrow. But what if I multiply by I? Turns out that's like rotating 90 degrees counterclockwise. If I rotate 2 times 180 degrees, that's the same as multiplying by -1. That's reversing the direction. So here I've got a number, it's like slightly bigger than 2, and I want to multiply by -I. So then I simply rotate in the clockwise direction. Notice if I do that 4 times, I'm going to get back to the number. That's because -I times -I times -I times -I, that's -I to the 4th power. That's 1. And I to the 4th power is also 1. So this algebra can be represented like this. Multiplying by real numbers stretches the arrow, or flips it if it's negative numbers. And multiplying by imaginary numbers, purely imaginary with no real part, is rotating. So if you have a complex number that has both a real and imaginary part, then multiplying by it means first you rotate by however much the imaginary part is, and then you basically stretch by however much the real part is. So that's how you can look at the algebra on the real numbers and the imaginary numbers. Together, they form the complex numbers. Now, you may wonder, what is the square root of I? We know that I is the square root of 1. What's the square root of I? That's like, what do you think? That's like rotating by 45 degrees. And if you do that twice, you've rotated by 90 degrees, which is like multiplying by I. So that's kind of cool. Complex numbers are used for solving all sorts of things. Now, you may ask an interesting question. Do these numbers really exist? The interesting thing is, throughout history, when the next set of numbers was invented, people were uneasy with it. You can imagine people might have had trouble accepting that negative numbers exist. You know, I've got a negative number of apples. What does that mean? Well, it could mean that I owe someone 3 apples, and when I get those apples, when I earn some apples, I'll have to give them away right away, and I'll get back to 0. Won't owe anything, right? But people were a little uneasy in the beginning until they started finding those numbers useful. The same thing, ancient Greeks were so disturbed, like I told you, that no matter how much you subdivided a ruler into equal parts, you can't have that same ruler measure both the hypotenuse and the side of this triangle. This triangle is just a simple isosceles right triangle. Same 2 sides are equal, but you can't have that ruler measure both of these, the side and the hypotenuse. But over time, people were able to use these numbers as square root of 2 and pi in very useful ways. So the imaginary numbers are called imaginary because people were already comfortable with the real numbers when they were invented. So they named the other axis the imaginary axis because they were like, well, listen, this equation, it's x squared, right? It's never really negative. You can't have x squared equals 3. But these numbers, they make it work out. So we're going to call them imaginary. We're going to work with them, but they're not real, right? It's an interesting question. When someone asks you, does this thing exist? You have to first define, what do you mean by the word exist? So, have you ever thought about what existence means? What does that word mean, exist? If I told you there's another universe out there, another world, it's filled with like green gremlins, okay? And you'll never discover this universe by any means that you can do. Nothing you do in this universe will let you see that universe, will let you deduce its existence or anything like that. You won't be able to know whether, if it's there. What does it mean for it to be there? If I told you that universe exists, how is that different than me telling you it doesn't exist? How is saying it exists different than saying it blah, blah, blah? If I haven't defined the word existence in terms of something that you already know, then that word is kind of meaningless. So we're not here to discuss the philosophy of existence, but what's interesting is that in math you don't need to care whether these numbers exist. What's important is that they're useful. They're useful in calculating things. They're useful in predicting things in the real world. And they've been useful throughout history. And that's why math has been useful. Take this, for example, this model of, in this case, Einstein's theory of special relativity, where you have here, or in this case, okay, you have space and time, sort of, you've got this field where you've got a planet orbiting a star, and at each point, there's an arrow, let's say a vector field, where it says, this planet's going to move with this speed in this direction, right? Give me a point, I'll tell you where the planet's going to move. So does this vector field, this gravity field, really exist? Is there a set of arrows somewhere that exists and the planet is consulting this, lookup table of arrows? Okay, I'm here. Where am I going to go next? Probably it doesn't exist in that form. There's no consultation going on. But it doesn't matter whether it exists or not. It's useful. It's useful as a model in order to do mathematical calculations. And the model that we make allows us to understand how the world around us works, and it can be used to predict certain phenomena and explain how they behave in terms of other mathematical structures. So that is why mathematics is useful. Now, whether these things exist or infinite sets of infinitely many numbers exist, that's not the point. The point is they're useful, and these constructs are used in the real world to do useful things. So, how are these sets used? Let's review. The natural numbers were used way back when for counting, adding up things, and stuff like that. The integers, z, that set is used for debts, measuring things that are below zero, like temperature or depth or anything like that. Q, the rational number set, is used for ratios. Ratios and subdividing, rulers and measuring units and stuff like that. So you can divide a pizza among 3 people. That set is expanded into a larger set which includes irrationals and rationals. That's called the real number line. And that is a continuous line that basically goes from negative infinity to positive infinity and everything in between. And people were using that for thousands of years, and then they wanted to find where a function equals 0. A function like x squared plus 1. If x squared plus 1 equals 0, then x squared has to equal negative 1. Where is that going to happen? Well, they invented numbers like the complex numbers. And with complex numbers, you can actually show that you can solve any polynomial equation for x. So no longer will you have this problem where you can't find an a that satisfies this equation. Any polynomial you give me, a polynomial is an equation consisting just of multiplication and addition. Any one of those you give me, I can solve it. I can give you a number that will make the equation true. So in this topic, we've explored the motivations behind why people came to use more and more complex types of numbers until they arrived at a set that they literally called complex numbers. And there are larger and larger sets, which I'm not going to cover in this video. But it gives you the idea. It illustrates one of the fundamental ways of thinking mathematically, to generalize a specific situation. Even the counting numbers themselves are generalizations that represent the idea that the type of item doesn't matter if all you care about is the number of items, right? Once you abstract away those details and you're only left with the size of the set, you can perform the same operation with a set of apples that you could perform with a set of oranges. So you can basically abstract away certain things, leaving only the essential things. That's another way of mathematically thinking about things. Similarly, the concept of a variable is the next level of abstraction because it represents the idea that particular numbers in a number set don't matter. It could be 3 plus 5 or it could be 7 plus 9. The rule still holds. And if all you care about is doing some operation with those numbers, then you can just use variables instead of like the the ancient Sumerians that gave examples and let you figure out the rule. So all you have to do is use the rules of algebra on that set. And the algebra that we developed includes addition, subtraction, multiplication, division, and raising to a power and roots. And it works everywhere in every set seamlessly, from the natural numbers to the complex numbers. And as we ran across different algebraic equations that we needed to solve for x, we needed to construct larger and larger sets of numbers because the previous numbers just didn't do the job. And what happened was the larger sets of numbers included the smaller set, and the algebra worked seamlessly between them. So in a way, we generalized the operations we already had on the smaller set to the larger ones in a seamless way. It's compatible. And that is just some of the examples in which mathematicians go from objects to numbers, numbers to variables, and in another sense, how they go from natural numbers to integers, integers to rational numbers, rational to real, real to complex. You build up all this machinery, and you have your notation, and then with just a few simple manipulations, you can say very complicated things. And they're always true because they're mathematical. Stay tuned for the next video. Thank you.